Hello everyone and welcome to the Database Applications in a Global World video lecture. This is Hossein Mohit, and in this lecture you will learn a summary of non-relational databases and explore some emerging technologies in the field of database and data management. As a reminder, this is just a summary lecture. You need to read your book thoroughly to fully understand and master these concepts. One important thing to remember about databases is that they are almost always function in connection with some type of software applications that provides a user interface. The only notable exception is Microsoft Access, which has built-in tools for developing simple applications. However, if you are using MySQL, SQL Server, or Oracle, you need to develop an application to provide the necessary user interface, making it easier for users to interact with the database. Regular users cannot be expected to run queries to retrieve information, and it is not advisable to grant direct access to the database for public or regular users. Many databases are distributed, and you will learn more about this in this chapter. Distributed databases, or those hosted in cloud structures, do not reside on a single server or computer. Instead, data is stored across multiple systems on the web. These systems are synchronized, connected, and work in tandem. It is also important to consider that the database technology must be compatible with the applications and devices it will connect to. For instance, you cannot design a database optimized for a supercomputer or workstation and then expect to seamlessly work with tables, smartphones, and regular personal computers. In this chapter, you will also be introduced to the non-relational databases. So far, our focus has been on relational databases, which are critical for managing the daily operations of a business. Towards to the end of this chapter, we will explore non-relational databases, including both those oriented toward analytics and those used for the operational purposes. Additionally, we will learn about the various hardware architecture for connecting database management system and applications, such as two-tier and three-tier and remote data server. In this diagram, you can see an example of the two-tier client-server architecture. On the left side, there are client devices such as computer, tablets, and cell phones. On the right side, we have a server that contains the database management system. This setup illustrates a non-distributed database management system, typically used by small to medium-sized businesses. These businesses can centralize their data because they have fewer customers and do not operate across many regions. In this model, database management systems and the data are hosted on a single server connected to the internet. The application programs running on the client devices connect to this database management server. This server then process the request and provide the necessary data to the client applications, which present the information to the users. This architecture is straightforward and work well for organization where data centralization is practical and sufficient for their operations. The two-tier client-server model is well suited for use within organizations where users are internal and the data can be centralized. However, if you want to make your database accessible to the public, you would need to use a three-tier architecture commonly found in the web applications. In the three-tier architecture, there is an additional layer between the client and database server called the application server. The application server acts as a bridge that enables web browsers and other public client to interact with the database server. In this setup, the database is still centralized within organization, but it connects to the application server which handles communication with external users. Unlike the two-tier model, where the application program resides on the client computers, in the three-tier model, the application server and the user interface are separate. The application server does not reside on the client computers. Instead, it is controlled by the organization. The client devices, such as web browsers, connect to the application servers, which manage requests, process data, and then interacts with the centralized database. This model provides an extra layer of security and control, making it more suitable for public access while still maintaining organizational control over the database and application server. In the next architecture, we explore the remote Windows data server with Open Database Connectivity, or ODBC. This architecture is ideal for the larger organization where different database management systems are used, and all these systems need to connect and work together to provide data access for users. In this model, various database management system technologies are linked using the ODBC driver, which act as a universal bridge for communication. ODBC allows to the application layer to interact seamlessly with multiple type of databases, regardless of their underlying DBMS technology. The application program can either reside on the same server as the ODBC driver on the separate server, depending on the organizational infrastructure. This design enables organization to access and utilize data stored across different databases throughout the organizational efficiently. ODBC, initially developed by Microsoft, has become an industry standard for connection applications to various databases. Although there are newer connection standards available, ODBC remains widely accepted and used, making it a reliable choice of integrating diverse database technologies. Other connection standards exist, but they are not as common as or as widely supported as ODBC. As our organization grows and integrates more deeply into the modern data environments, we will likely start to encounter non-relational databases and non-relational data sources. ODBC, which stands for Open Database Connectivity, cannot directly handle non-relational databases or unstructured data. So we need a different approach. This is where we use the object linking and embedding databases, OLEDB, which it comes to the play. OLEDB is an object-oriented interface designed to wrap around the ODBC and extend its capabilities. It allows for integrating with various types of data, including non-relational database and unstructured data sources, by providing a standard way accessing and linking data from different systems. It supports data access from object-oriented language and can handle a wide range of data sources, not just traditional relational databases. In a sense, OLEDB acts as a bridge, providing a consistent interface that can link and integrate all kinds of data, regardless of their structure. It allows the application layer to interact seamlessly with both relational and non-relational data, offering a unified data access solution for complex environments. When interacting with the database management systems via the web, the SQL statements are often generated by the browser as a part of the web application's commands. These SQL statements are then sent to the server within the browser packets to request or manipulate data. The server processes these requests either through the sequential processing or by using a cursor. A cursor is essentially a pointer to the current active records in the result set, allowing the applications to navigate through the return data efficiently. However, embedding SQL statement directly in the web applications opens up a potential security risk, one of the most common being SQL injection attacks. SQL injection is a straightforward yet effective method used by hackers to gain unauthorized access to an organization's database. It exploits poorly programmed web applications that inadequately handle user inputs. The attack works by injecting malicious SQL code into the application's input fields, which then gets executed on the server. The basic idea behind the SQL injection attack is to replace the legitimate SQL code embedded in the web applications with malicious SQL code designed to manipulate the database. If the web application's user accounts has broad permissions, this malicious code could allow the hackers to access, modify, or delete sensitive data. For example, if the applications does not properly restrict what user can do and allows direct execution of the embedded SQL code, attackers might be able to retrieve unauthorized data or even gain full control over the database. To prevent such attacks, developers can use stored procedure and triggers, which provide a layer of abstraction and control over direct SQL execution. So one of them is the stored procedure. A stored procedure is the predefined reusable routine that include both procedural logic and SQL statements. Unlike raw embedded SQL, stored procedures are executed within controlled inputs and are not easily manipulating by external users. They are invoked by the specific procedures called from the applications rather than direct user input, which makes them more secure. The second one, a trigger, which a trigger is an automated action that is set off by specific events in the database, such as insert, update, or delete operations. The trigger defines the event to be monitored and the actions to be performed when the event occurs. Triggers help enforce business rules and ensure data integrity as they execute predefined actions automatically based on specific conditions. By using a stored procedure and triggers, developers can minimize the risk associated with the SQL injection attacks, as these techniques limit direct user input and enforce more secure access pattern to the database. Distributed databases are increasingly common in modern systems, especially when dealing with large amounts of data. Diverse database management systems or geographically dispersed client and customers. When customers are spread across the globe, it becomes essential to have database server and application servers closer to them to reduce latency and provide better service. There are three main approaches to distribute databases: data replication, horizontal partitioning, and vertical partitioning. Replication involves creating copies of entire database at multiple locations. When data is updated at one location, other copies may temporarily hold outdated data until they are synchronized. Synchronization ensures that updates are propagated across all copies of the database. But this process can be complex as it requires locking mechanism and coordination to maintain consistency. The main advantage of replication include location independencies, built-in backup, as such copy server as a backup, and suitability for transactional processing. However, it can be complex due to the synchronization and involves higher cost because full copies are stored at every location. In horizontal partitioning, the records of a table are split across different database server based on a specific criteria. For example, customer data from the US might be stored in the US-based server while European customer data is kept in a European server. This method offers location-based independency, reduces storage cost as not all data is replicated across every server, and simplifies design when partitioning by region. However, it can be challenging when dealing with customers who travel frequently and backing up the system is more difficult compared to the full replication. Vertical partitioning involves splitting columns or fields of a table across different servers. For instance, some columns of a customer table might be stored on one server while others are on a different server. While vertical partitioning can reduce storage costs and allow for a specialized data storage, it also increases complexity, especially when splitting columns of a single table. It is simpler to manage if the whole tables are partitioned rather than individual columns. In some cases, a combination of the replication, horizontal partitioning, and vertical partitioning is used to create a flexible and efficient distributed database system. An emerging distributed database method that follows the replication approach is blockchain technology. Blockchain introduces a key feature, transparency. It ensures that all transactions are transparent and viewable by anyone with access and guarantee that no record is ever lost because multiple machines maintain identical copies of a transaction data. The data structure primarily consists of transaction records, which are usually textual and relatively small in size. Blockchain's main advantage include the high level of data integrity, as transaction cannot be altered or deleted, and robustness, as multiple copies prevent data loss even some nodes fails. In summary, distributed databases offer various methods for dividing and managing data across different servers, and the choice of method depends on the organizational specific needs, including cost, complexity, and data access requirements. XML or Extensible Markup Language is the key technology used by most databases to communicate within the application layer. When databases output data, they often format in XML, a markup language that provides a structured way to describe data. Unlike HTML, which is designed to display data, XML is a very flexible and allows programmers and developers to define their own structure using custom tags. XML documents typically consist of header and a body. In the header, you may find the document type declaration, DTD, which was used in older technologies, or and XML schema definition, XSD, which is the preferred method today. XSD defines the structure of an XML document, specifying what each tag means and allowing developers to create their own custom tags. This is called an XML schema. The XML data sent from the database to the application layer is often processed and transformed for display using XSLT, Extensible Style Sheet Language Transformations. XSLT formats the XML data into the readable and organized formats on web browser, making it visually appealing and user-friendly. Another important concept you may encounter when working with distributed databases and application layer is web services. The idea behind web services is to separate the processing of data, which happens on the server, from the user interface, which runs on the client device. This is similar to how XML and web browser works together today. Although web services are becoming less common, they were the foundation for modern browser-based XML interactions and played a significant role in connecting databases to the application layer. Even now, XML is still used in the web services as the primary tool for data delivery and data exchange between different systems. As I mentioned before, in this course, we focus primarily on relational databases, which are essential for managing business transactions and daily operations. However, when it comes to the strategic decision making and analyzing organizational performance, a different type of data structure is needed, called a data warehouse. Data warehouses are typically not normalized and are created by reorganizing existing business transaction data from relational databases. They are designed for analysis rather than daily transaction processing. A data warehouse is characterized by using subject-oriented, integrated, non-volatile, and time variant. By subject-oriented, we mean that the data is organized around a specific topics such as customers, illness, or insurance in a healthcare context. Instead of having separate table for customers and illnesses, a data warehouse might include a table that combines customer data with illness data. This approach does not focus on a strict normalization like a relational database because the goal is to provide a comprehensive view for analysis. Data warehouses are also integrated, meaning they combine data from various sources across the organization, including different databases and even external sources. This integration provides a unified view of the organization's data, making it easier to analyze and gain insight. Another feature is non-volatility, which means that data in a warehouse is not frequently updated or modified by end users. Instead, it is loaded through the process called ETL, extract, transform, load. ETL extracts data from relational databases, transform it as needed, and load it into the data warehouses. Because the data is not the subject to regular update, issues of data integrity are less of concern. ETL can be done in batches, such as weekly or in a smaller interval for real-time updates, providing decision makers with up-to-date information. Lastly, data warehouses are time variants, storing historical data with timestamps. This allows for the analysis of the trends over time, which is the crucial for understanding patterns and changes in the business metrics. Having time variant data help decision makers observe the evolution of the business performance across different periods. In summary, a data warehouse is optimized for complex analysis and reporting, offering a comprehensive integrated view of data from various sources, unlike relational database that focus primarily on transactional processes. Here is the diagram of the ETL process. As you can see, extract, transform, load will collect data from internal and external sources and load it into the enterprise data warehouse. The data warehouses can also have data marts. Data marts are essentially functionally oriented data warehouses that design to make the analysis and analytical queries faster and more focused. Each data mart typically has a star schema design, which you will learn about it in the next slide. So, a star schema is the data structure that consists of the central fact table connected to the multiple dimension tables. In this example, the fact table is the sale table, which includes details like product ID, period code, customer ID, size code, sale quantity, sale amount, and cost amount. The surrounding dimension tables provide additional context for these facts. For instance, the product dimension table contains information about the products. The customer dimension provides customer details. The size dimension indicates the size of the purchase, and the period dimension covers the time period of the sale. The design of the fact table and its dimension is based on the business requirements and logic. So even businesses within the same industry might have different fact tables and dimensions tailored to their needs. As I mentioned earlier, a star schema is often used within the data marts. Data marts are a specialized, functionally focused data warehouses designed for specific areas of the business to speed up analysis and streamline analytical queries. In addition to the star schema, other structures like snowflake schemas and data cubes can also be used to organize data warehouses and data marts. The Snowflake schemas is more complex and newer structure compared to the star schema, while data cubes are older structures. Despite these alternatives, the star schema remains the most popular and widely adopted method for organizing data in data warehouses. For more details on Snowflake schemas and data cubes, refer to your textbook. There are two general approaches to designing data mart schemas, including the star schema, the top-up approach, and the top-down approach. In the bottom-up approach, we first build smaller focused data marts and then later consolidate these data marts into a larger, comprehensive data warehouse. One advantage of the bottom-up approach is that data marts can be developed and implemented more quickly, enabling faster analytical decision making. However, the main disadvantage is the potential difficulties encountered when integrating all these individual data marts into the unified data warehouse, which can be challenging. On the other hand, the top-down approach starts by building a complete data warehouse first, followed by creating a specific data mart tailored for particular business functions or needs. The advantage of this method is that it is typically results in a well integrated and comprehensive data warehouses. However, it can take longer to implement and may involve more complexity. Once your data warehouses or data marts are set up, the next step is the extract, transform, and load process, ETL process. The ETL process can be complex and may lead to data integrity issues and inconsistencies if not carefully designed. It is crucial to ensure that the data being transferred is not altered in a way that compromises its integrity or accuracy during ETL process. Interest in data warehousing and online analytical processing OALP tools to support business intelligence and various analytics has led to the demand for SQL extensions. The two most important extensions are Rollup and Cube, which introduce new clauses and syntax to existing SQL. These extensions allows users to perform more advanced queries. While each DBMS provider has its own set of SQL extensions, Rollup and Cube are commonly supported across many systems. It is important to note that relational databases are not designed for analytical processes. For most analytical tasks, you need to extract data from these transactional databases and transfer it into the data warehouse. Data warehouse enables organizations to slice and dice their data and query it for it from different perspectives. However, even data warehouses are not typically designed for advanced predictive analytics or sophisticated descriptive and exploratory analysis. When it comes to the data analytics, a subset of data science, there are two general methodologies: unsupervised and supervised learning. Unsupervised methodologies are also called exploratory or descriptive approaches. Examples include clustering, attribute weighting, anomaly detection, and association rule analysis. In clustering analysis, the goal is to group data into the different clusters, with the most common method being k-means clustering. Attributes weighting involves determining the importance of each attribute in relation to the target outcome. Anomaly detection, often uh, used in security applications, aims to identify deviation from the norm to detect unusual behaviors or events. Association rule analysis looks for patterns of items that frequently occur together, as seen in retail setting and recommendation systems like Amazon's product suggestion. In supervised learning, the focus is on predicting future outcomes based on the past data. This involves using historical data to identify patterns and make predictions. Supervised methods are typically divided into two main categories: classifications and regression. Example of classifications method includes decision trees and neural networks, while regression methods include linear regression and logistic regression. To learn more about these methodologies and conduct this type of analysis, you would need to take a data mining course in the IS department. These analysis cannot be performed directly on relational databases. Data must first be extracted from these databases and then analyzed using a specialized tools and platforms. Even data warehouse requires appropriate extension for conducting such advanced analytics. Big data is the buzzword and concept that revolves around three main pillars, often referred to as the three V's: volume, velocity, and variety. Some sources, including your textbook, add two more V's, making it as a five V's of big data: veracity and value. Let's start by discussing the three main ones. The volume refers to the sheer size of a data. It is a massive data that can be hard to comprehend. Once the data volume surpasses a few thousand terabytes, it becomes unimaginable. This is where the term big data originates. Velocity is the speed at which data is generated. Millions of pictures and videos are uploaded to platforms like Instagram and Snapchat every hour, and millions of tweets are posted every minute. Similarly, in online retail, millions of transactions may occur per minute or hour. The fast pace at which data is created is defining aspect of the big data. Variety refers to the different type of data we now deal with. We are no longer only working with the structured data like text or numbers. We now handle unstructured data such as voice, images, and videos. Data can come from diverse sources and take various forms, making it more challenging to organize and analyze. For example, your Facebook data includes picture, videos, text, posts, uh, likes, and reactions, all different type of data related to you. In addition to these three, the veracity of the big data is crucial. Veracity refers to the accuracy and reliability of the data. When data is being generated at the high volume and speed and coming from various sources in different formats, ensuring its accuracy is significant challenge. Lastly, the value of the big data refers to the worth of the information it provides to the organization. It is one thing to collect massive amounts of data, but it's another to make sure it is valuable for business decision making. Data preparation and analysis require significant effort, so you need to determine if the insight gained are worth the investment. Due to the challenges of the volume, velocity, variety, veracity, and value, specialized platforms and languages have been developed to handle big data. Giving the high volume of Given the high volume and velocity, big data typically requires a distributed database system. Hadoop is a leading platform that addresses these challenges. Originally developed by Google, Hadoop is widely used by companies like Facebook. It features a distributed file system that stores the dataset across multiple servers and uses a process called MapReduce to handle computational task efficiency. NoSQL databases are also a critical part of the big data. Within the NoSQL movement, there are several type of databases. One of the most common is the key value databases, where data is stored as a key value pairs. These pairs are organized into the buckets similar to tables in relational databases. The key server as the unique identifier for the data value, much like a primary key in a table. The value can be anything from simple string of the text to more complex data like picture or videos. Another type is document databases, which are similar to the key value databases but store data in a document format, typically JSON, JSON, or XML. Wide column databases are all also similar to the key value stores but group related columns together, allowing for more efficient data retrieval. For example, information such as first name, last name, and address might be stored in a common column family. Lastly, graph databases differ fundamentally from the key value based databases. They use graph theory to model data, focusing on the relationships between nodes, which is the data points. Uh, Also, early databases use the graph-like structures But modern graph databases are more advanced and are not based on the physical addresses of the data. They are particularly effective for analyzing relationships, making them ideal for applications like social network analysis and fraud detection. Okay, so we have now reached to the end of this video lecture. I hope you have learned something new. So just keep in mind that this was only a summary lecture, and although it was longer than some of the others, you still need to read the textbook to gain a deeper and more comprehensive understanding of the concepts we covered today. Please email me if you have any question. Good luck.